Very good morning. The last lecture we have studied up to the Arrhenius equation k is equal to a into e to the power minus ea divided by rt. This is the Arrhenius equations. We have another Arrhenius equations in the form of constants, that is constant of integrations c. These equations can be shown in the form of ln k to the ln k is equal to minus ea rt plus c. So in these regards, these two are the most important formulas of the Arrhenius equations. Next, it is the minimum energy with the reactant molecule. Example, EA means energy of activations for acid hydrolysis for methyl acetate is 64.56 kilojoule per mole. This is the energy profile diagrams. On the axis, on the one axis energy, another axis progress of the reactions. This diagram indicated that as the energy increases or as the progress of the reaction increases, energy is also increases, but energy increases up to activated complex, that is activation of energy up to the activated complex, and it is reached up to the activated complex. Then from the activated complex it drop back to the lower level as the transition states converted into the products. Energy is the high at the transition state because at that time it is on the peak of the energy, and as it downs, the product energy increases and the formation of the product is also in the process. So the reactants, activated complex and the products, according to Arrhenius equations, K is equal to rate of the reaction is equal to A Arrhenius constant dot E to the power minus EE activation energy divided by R T. T is the temperature constant, R is the constant. These two are the constant terms. So temperature is variable, K is the constant. At high temperature, e to the power minus EA RT is the large. As the high temperature is high, the value of e to the power minus EA divided by RT is large, because as we take the T, the logarithm of E convergence factor will be the high, means the E to the power minus EA divided by RT is the large, hence the rate constant K has the value high. This explains the decreasing the reaction rate with the temperature. Means the as the temperature increases, means the value of E increases. As the value of E increases, the value of K is the decreases. Hence the rate of the reactions and the temperature are the reciprocal to each other. Next, if the reaction has a high EA value, if the reaction has high EA value, if the reaction has high EA value, its rate will be the low and vice versa. Its rate will be the low and vice versa. On plotting the graph of log K versus log 1 upon T of Arrhenius equation, on plotting the graph of log K versus log 1 by T of Arrhenius equation, log K is equal to log A is equal to minus EA divided by RT. Log K is equal to log K is equal to log EA divided by RT. Log K is equal to ln converted into the log A. Ln K, applying the log on the both sides, so ln K converted into log K, ln A converted to log A, minus EA divided by RT converted into minus EA divided by 2.303 RT. Log versus 1 by T should be the straight line with the intercept log A on the log K axis, and the slope is equal to minus EA divided by 2.303 RT. This is the slope can be found out by using this formula. Minus EA, energy of activation, 2.303 is the constant term, R is the constant term, and T is the variable, whatever it may be, that value is should be written and find out the slope. So in the graphical representations of the log K and 1 by T degree of the reactions, slope is equal to minus EA divided by 2.303 RT. This is the graphical representations. Next is the concept of the energy of activation. Concept of energy of activation. Arrhenius qualified the effect of temperature on the rate of the reactions. Arrhenius quantifies the effect of temperature on the rate of the reactions. It gives the relation between the rate constant and the temperatures, and how it is correlated, how it will affect as the temperature increases. EA means energy of activation is called as the energy, EA is called as the energy of activation of the reaction, which is the minimum amount of the energy in which reactant molecule must occur, in which the reactant molecule must occur. According to the kinetic theory of the gases, molecules are always in the state of motion, resulting in the molecular collisions. When the reaction takes place, molecule undergoes the collision. The frequency factor and the given total number of the collision taking place in unit volume in unit time. According to kinetic theory of gases, molecules are always in the state of motions. For the considering these equations, we can understand one of the example of the closed chamber in which some gases are released. As the some gases are released, these gases are continuously colliding one another, continuously rotating, means that they are continuously in the state of the motions resulting in the molecular collisions. Resulting in the molecular collision, when the reaction takes place, molecule undergoes the collision. The frequency factor A gives the total number of the collision taking place in the unit volume, unit time. Next point, molecular passing energy. Molecule passing energy equal to or greater than EA. Molecule possessing the energy equal to or greater than EA means the energy of the molecule is greater than the activation energy, means the no need of the activation energy at that time. The alone can undergo the effective collision resulting in the reactions on which the rate of the reaction depends. Okay, so in this case rate of the reaction depends on the concentration of the reactant when the energy of the reactant is greater than activation energy. The effective collision can be correlated, the total collision by the equations. Effective collision can be correlated, total collision by the equation effective collision is equal to e to the power minus EA divided by RT. That is, the effective collision is equal to total collision into the power e to the power minus EA divided by RT. Also, the reacting molecule can be correlated to the number of collision molecule by the equation reacting molecule is equal to e to the power minus EA divided by RT. Hence, the fraction of total number of molecules that possesses energy of activation is directly proportional to the factor. It increases with the temperature and leads to the increase in the rate of the reactions. So, hence the reactions of total number of collision molecules that passes energy of activation is directly proportional to the factor that increases with the temperature and lead to the increase in the rate of the reaction. According to Maxwell's Boltzmann distribution of the velocity, the majority of the molecules travel with the average velocity of the molecule travel with the average velocity which is constant at the given temperature. If the fraction of the molecule passes particular energy, E can be plotted against the kinetic energy per mole for two temperature and T2 difference at 10 degrees centigrade as shown in the figure. So, these all are about these factors in the activation energies, and the collision frequency factor given total number of the collision taking place in the unit volume in the unit time. Molecule possessing the energy equal to or greater than the activation energy alone can undergo the effective collision resulting in the reaction on which rate of reaction is dependable. The effective collision can be correlated, the total collision by the equation effective collision is equal to this type of collision is dependable. This is a diagram is representation of this experimental potential energy and kinetic energy, that is energy of activations. T1 are the temperatures, T2 are the temperature, two variable temperatures, and then the product formation, that is dotted lines. This is all about these relations, activation energy, and in the next lecture we will see the experimental estimation of activation energy. Thank you.